Everyone to the second session of the Revman. Last week we had a robust discussion where we introduced Revman, introduced meta-analysis in Revman, some of the pitfalls, challenges, some of the merits of using Revman, and we went through meta-analysis using meta-analysis for ratio outcomes, so dichotomous outcomes like risk ratios, odds ratios, you know. So before we get started, before we dive in, I want to ask, does anybody have any initial questions that you would like us to quickly address before we go on? Today, what we are going to do is that we are going to look at meta-analysis using for continuous outcomes, such as mean differences, and we would also look at meta-analysis for meta-analysis for the heterogeneity and inference analysis, sensitivity analysis. Hopefully, we can go through all of that in the next 90 minutes. So any questions before we dive in?
Yeah, I have a question.
Yes, please.
Now, assuming that I want to pull studies for my meta-analysis, and I come across studies like that has the same effect, the same outcome, but they are either case control study or cohort study, in which the point estimates, one is odd, one is risk. So how am I going to, if I have to pull those studies because they are actually having the same exposure, the same outcome, but different point estimate? How can I include that study in my meta-analysis? Am I to include the risk, the study that deals with risk separately, or the study that deals with associations separately? Or can I combine the two studies, since both exposure and outcome are actually my point of reference, and they are similar to what I want to do?
Excellent question. And I think that from the way you've asked the question, you already have some suspicion of how you will go about it, and most of your suspicions are correct. So you asked, can you pull those studies together since they have the same exposure outcome relationship? And the answer is maybe, and I'll explain. So if they have the same exposure outcome relationship, and one has reported the estimate is in odds ratio, the other has reported the estimate is in risk ratio, you cannot pull those together, right? Some people do, but it's not ideal. What you can do is that you can recalculate the odds ratio. Say maybe 5 studies have odds ratio and maybe one has risk ratio. You can calculate the odds ratio from the risk ratio. Or maybe, depending on whichever one that you want to report in your final study, you calculate that one from the one that you're giving. So the question will be, how would you do that? And one way is to go back to the raw data. So sometimes the study will provide the raw data, and you can use the raw data to calculate the estimate. So let's take the example that some studies have reported risk ratio, maybe 5, and one study has reported odds ratio. But the study that reported the odds ratio, you have the raw data for that study. You will use the raw data to calculate the risk ratio for that study. That's one way. Another way to do this, there's a formula, and I can dig that up and share it after the class. There's a formula that you can use to go from risk ratio to odds ratio or vice versa if you know the prevalence of the outcome in your study. Let me take that again. There's a formula that you can use to go from risk ratio to odds ratio and vice versa, right? If you know the prevalence of your study. So typically, we will do either approach, either use the raw data or use that formula to estimate and go from one type of measure to the next. But you shouldn't ordinarily report risk ratio and odds ratio in the same meta-analysis. Another thing that we often do is pull them separately. It depends on the number of studies, and especially if you have 5 core studies and you have maybe 6 case control studies, then you could pull the case control studies and the cohort studies separately, and report them as separate estimates. That's another approach that you can use. But if you want to pull them together, then you choose one measure type and convert the others to that one and report them. Oftentimes, if you pull the studies separately by study type, you might see patterns that emerge. Okay, where maybe cohort studies are reporting one direction, while case control studies are reporting another direction, and understanding the challenges of the different study designs can then help you understand the results that you're seeing. I hope that helps. I think we have another person who has a question. Umfang, do you have a question? You still have your question?
Yes, I wanted to ask exactly what you asked. If maybe I'm doing a meta-analysis of randomized control trials, and I find out that out of the 7 studies I've decided to work with, 3 reported using the risk ratio, and 4 using the odds ratio.
Okay.
So I think you've clarified that I need to make use. I can make use of the raw data, that's the exposed cases, unexposed cases, to pull my estimate using either fake measures. Thank you.
Yeah, you're welcome. There is another point I should make.
Hello. Please, I also
yes,
want
ask your question.
it's just like a contribution, just as also a reminder that you please give us the formula that we can use for that conversion if we have the prevalence. I think it will go a long way to help us. And I also think the major challenge too with this kind of approach will be getting the raw data.
Yes, that's exactly correct. So it depends on what has been reported in this study. I will share that formula. Thank you. Another point I want to make is that if you have risk ratio and you have hazard ratio, we often pull those together. They're not exactly the same, but they are closer than if it was odds ratio. So if you have the risk ratio and hazard ratio, we often pull those together and just call them all risk ratios, but we don't do that for odds ratio. All right. Thank you very much for that question. So let's dive in. So today we are going to look at mean differences and something called standardized mean differences in Revman. Okay. And I will explain what that means in a moment. So just a quick recap. We said that there are multiple steps, 9 steps for meta-analysis. And today we are looking at data synthesis. The bulk of the live sessions are focusing on data synthesis. And we started from last week. We did it in Revman and SPSS, and then we're continuing the discussion in Revman. Tomorrow we will have a repeat of the SPSS session. Some people were unable to participate maximally in the SPSS session because they didn't have the latest version of the SPSS. So hopefully by tomorrow you would have installed the trial version if you want to, and if we have a large enough crowd, then we'll teach the class. Otherwise, we might skip it. All right. So last week we looked at how to create a pooled estimate for ratio measures in Revman, as well as we looked at funnel plots in Revman. Okay, and today we would look at pulling difference measures, mean difference in Revman, as well as the funnel plots, and hopefully we might be able to look a little at how Revman addresses heterogeneity. Okay, so this is just a welcome screen again. So so we're doing this exactly the same question. If you saved your progress last week, then you can just reopen your Revman file and then we can dive in. But if you didn't save your progress, that's okay too. We will. I already emailed you a version of the Revman file that I used last week, and we can use that to get started. But before we go on, I just want to tell you a little bit about the meta-analysis of mean differences, some of the key concerns that you have to bear in mind. The first is that there are different ways that we do it, that we think about the mean difference. So if you think about the mean difference, right, it is that you have the mean in the treatment arm and you have the mean in the control arm. And then you look at the difference. That's simply what it is, mean difference. So a mean BMI in treatment arm maybe after 6 months of exercise, and mean BMI in the control arm and then you look at the difference. Another way that we often think about the mean difference is mean at baseline. So maybe people who are exercising in an exercise study, the mean BMI at baseline, you have 100 people, you calculate the mean of their BMI at baseline, you calculate the mean of their BMI at the end of the study, and you look at the difference between the mean at baseline versus at the end. That's how we often obtain mean difference. Now, we can take that mean difference and pull them together across multiple studies. So maybe 5 studies, 10 studies, and the estimate you will usually get is called a mean difference, but that's often called a weighted mean difference. And the reason it's called a weighted mean difference is because if you remember when we talked about the fundamentals of meta-analysis, we said that it's really just a weighted average. Okay, we said that you would think about the estimate as the estimate across each of the studies divided by their standard error. So you're weighting based on the population size, number of participants in the study. So it's fundamentally a weighted average. Okay, so that weighted average, we call it the weighted mean difference. And oftentimes when people do meta-analysis and you just see them say they report a pooled mean difference or they report the mean difference across the studies, what they're really talking about is this weighted average, okay? This weighted mean difference. But there's another type of mean difference, and that's the standardized mean difference. I'll talk about that in a moment. But when we want to do a meta-analysis of mean difference, there's a number of decisions you have to make. You want to see, should I use a weighted mean difference or should I use a standardized version? The other question, and these are the other questions that we looked at when we did the ratio measures, is what kinds of weights should we use? Fixed effects, random effects, raw data, pre-calculated effect sizes. Those are the same as what we saw last week. But this week, there's an additional layer on top of that. And that is, should I use a weighted mean difference or a standardized mean difference? Okay. So like I mentioned earlier, the weighted mean difference is really just the weighted average of the mean differences. And it's very similar to what we saw last week when we looked at fixed effects and random effects. And if you remember, we said the fixed effect only incorporates the weight from the standard error, while the random effect incorporates the weight from the standard error as well as the extent to which the studies vary from one another. So you can have fixed effects and random effects for weighted mean difference. You can have fixed effects and random effects for standardized mean difference. The difference between the weighted mean difference and the standardized mean difference is that we have the weighted mean difference, then we divide it by its standard deviation. Okay, you take each study, the difference of the mean for each study, you divide that by the standard deviation. And the reason we do that is sometimes we are looking at estimates that are measured on different scales. Okay, when the outcome is measured on a different scale, we will often use a standardized mean difference. Remember, we said that you should define the exposure and the outcome to be exactly the same, right? In some cases, we will allow you to be a little liberal with how the outcome is defined. Okay, so the outcome might be adiposity. So that's the example that I use here, where the outcome is adiposity compared to if the outcome was BMI. Now, adiposity, there are many ways that we can measure adiposity. We would often use BMI. That's the most commonly used, but some studies, maybe because they have higher precision tools, they're able to calculate the fat-free mass, they're able to calculate the lean mass, they're able to calculate other things. And if you think about adiposity as your outcome, right, you want to pull those together. Remember that BMI and fat-free mass and all of those, they're measured on different scales. You cannot pull them together using a weighted mean difference. A standardized mean difference allows you to get around that a little bit. So if you have maybe 3 studies reporting based on BMI, 4 studies reporting based on using fat-free mass, you can pull those together and your outcome will be adiposity. But to do that, you take each value and divide it by its standard deviation. Okay, You take each value. So if the mean is, if the mean BMI is 25, okay, and the standard deviation is 10, you divide that 25 by 10. And if the mean fat-free mass is maybe 40, and then the standard deviation is 10, you divide that 40 by 10. That's how you will then get a measure that's a standardized difference, a standardized mean difference that you will then pull. I hope this is clear. This is a very important distinction to get. Let me give you another example. So sometimes we use scales in measuring our outcomes, right? So maybe you're looking at the extent to which having a peer group influences the risk of depression. So maybe you have peer counselors, it's an HIV program, and you're looking at the extent to which having peer counselors impacts depression. So you assign one group, you give them peer counselors, another group, you don't give them peer counselors, and you assess depression at the end, right? So you have a study that looks like this, and there's maybe 7 studies like that all over the world, and you want to pull those studies together. Now, in some studies, maybe studies conducted in Tanzania, they have used one particular type of depression scale, maybe CESD, okay? In another study, maybe in Sierra Leone, they have used another type of depression scale. Maybe they use a Hamilton scale. And you want to pull the scales, the CESD and the Hamilton scale, or maybe GHQ 12 or whatever. And you want to take all these estimates and use them together in the same meta-analysis. For you to be able to do that, because these are measured on different scales, right? And you want to look at the mean difference for each of those studies, but you know that they are all measuring depression. You already know that. The issue is just that they're measuring it in different ways and they have different units. Then you might be able to use a standardized mean difference. So remember that we said that, that you have to define that the outcome and the exposure, they have to be the same. So in this case, we are saying the outcome is depression, but that depression is measured in different ways. The standardized mean difference allows us to get around that a little bit. This is the most important concept you have to take away from today's class. Questions? So someone said, what is the difference between dichotomous and continuous outcomes? Yes, please go ahead.
So to confirm, so it means that we are going to have 7, let's say there are 7 studies. So that will be 7 mean estimates that will then standardize each one of them.
Exactly.
Yeah, okay,
yes.
Thank you very much.
Yeah, that's exactly what it is. 7 estimates, you standardize each one, and then you pull the standardized estimate. Excellent question. Someone asked what's the difference between a dichotomous and a continuous outcome. A dichotomous outcome is maybe you take hemoglobin. Hemoglobin goes from 3, up all the way until 20 in the normal range. And anemia is defined by hemoglobin greater than 11 or less than 11. So if you take that between 3 and 20, and it's a continuous outcome because it goes from 3.1, 3.2, 3.3, it continues like that all the way to 16, 16.1, 16.5, all the way to 20, okay? That's the range of possible outcomes. Now, if you break it in two, and you have some people who are above 11 or below 11, that's a dichotomous outcome. That means that you've broken, you have 2 possible values for that outcome. Another way to think about a dichotomous outcome might be something like, BMI, where someone is either obese or not obese. There are other types of categorical outcomes as well, where like maybe red versus yellow, which are not necessarily dichotomous in the traditional sense, but you can also pull them the way that you can pull dichotomous outcome. Someone asked if it is possible to combine studies that use dichotomous outcomes and continuous outcomes. And my advice is don't do it if you can avoid it. don't do it if you can avoid it, because it's hard to interpret. Okay, there are some tools that purport to be able to do so. There's the Hedges G, there's the Cohen's, but it's hard to interpret. And if you cannot interpret your meta-analysis, what does it mean? The pooled estimate, what does a pooled estimate mean? Are you going to get a pooled estimate on a continuous scale or a dichotomous scale? It's hard to interpret. So the preference is to move away from tools like that and to wait until you have enough data to be able to pull continuous outcomes alone and dichotomous outcomes, alone by themselves. All right. So let's dive into Revman. I'm going to share my my Revman now. So if you have your Revman open, to the first one we want to look at is weighted mean difference based on pre-calculated data. Okay, the way we have done it, pre-calculated data first, then raw data next. Pre-calculated data means that we already have an Excel spreadsheet, and this is our Excel spreadsheet, that has the data that we need. And if you scroll to the end, this is the yellow ink that we used from previously. If you scroll to the end, you will see that we have these mean differences. Okay, we have these mean differences and we have the standard error of the mean difference. Okay, so I can highlight this, maybe highlight this in green, yeah, maybe green, to show that this is what we're focusing on today. This is the mean difference. So you have looked at, you have conducted media campaigns in one group of villages versus another group of villages, and you looked at the mean intake of fruits and vegetables in the treatment group versus the mean intake of fruits and vegetables in the untreated group, and then you take the difference. So that's how we obtain this mean difference for each study. And now if you want to pool these mean differences together to obtain a pooled mean difference, okay, that's the focus of today's analysis. All right, so if we go to our Revman, if you go to the Revman, if you click on this data and analysis, you can find this green sign, the green sign that comes up. If you click, you can click that, or if you can right click and add a comparison. Okay, if you add a comparison here, you type in maybe continuous, or you can type in media campaigns. I like to use informative inputs. Okay, media campaigns, fruits, intake of fruits and vegetables, or fruits and vegetable intake. All right, so this is not dichotomous where we're saying greater than 5 plus, So fruit and vegetable intake, you click next. Here it says, what do you want to do? So you add an outcome under the new comparison. All right, and then you click continue. This is an important point to pay attention to, because this is what changes what happens to your to the prompts going forward. If you click dichotomous is the one we looked at last week, but in this case, we're interested in continuous, okay? But because you're using pre-calculated data, you will go back to the generic inverse variance. Remember the last week when we used pre-calculated data, we used the generic inverse variance. Here as well, you would use the generic inverse variance, and then you click next. But before you go, pay attention to what this is saying. It says that you enter an effect estimate of your choice and its standard error, okay? Effect estimate of your choice and its standard error. All right, so you click next. Now you have to name this. You have to name this, and we can call it fruits and vegetables servings per day, or we can call it weighted mean difference. So I'm calling it WMD servings per day, okay? Or we can call it weighted mean difference using pre-calculated data, okay? This is pre-calculated data. And you have the experimental arm and the control arm. So you click next. So This point, you have to also pay attention to this point because what you do changes the results. There is inverse variance is the only option that you have here. You can either choose the fixed effect or the random effect. So if you choose fixed effect for starters, you can choose the effect measure here. And this might be the mean difference, the standardized mean difference, risk ratio. So you choose mean difference and you click next. Okay. So here, just leave it as is, totals and subtotals, 95% confidence intervals. If you want to enter the sample size, you will click this one, but click next. Okay. And then here, this is the left graph label, the right graph label. We can leave this or we can swap it out. Remember that this was where we had that issue the last time. So let's leave it for now and we can correct it when we come back. Here is an important point to pay attention to: the scale. Okay, the scale tells you about how, what does a graph look like? Is it a graph that goes all the way to 100? So from negative 100 to 100, or, so you can change the scale. We don't expect the fruits and vegetable intake people are not eating more than 5 or 10 servings per day. So I'm going to change this to 5, or you can wait and edit it at the end. Whichever one you do is fine. Here you choose how you're going to sort and you click next. All right. The next thing is, what do you then do at this point? Do you want to edit the new outcome or add a subgroup for the new outcome or add study data? So I'll say add study data. All right. So if you click next, now it comes up with the 7 studies. Remember, we had 7 studies that we had pre-specified that we're going to add data for. So then now if you select all those 7 studies and you click finish, okay, you click finish, now it gives you this. And you can notice that here we have mean difference and standard error. The last time we had, I think we had effect estimate or something like that and standard error. I'm just going to show you what we had. So here we had log risk ratio and standard error. Okay, if you double click this, it will bring this up. But here today we have mean difference and standard error. So we can go into our Excel sheet. So remember that, note that here we're not using log at all, because the mean difference is on a scale that is symmetrical. It goes all the way from negative infinity to positive infinity. So I will just copy all 7 studies, 6, copy all 7 studies and paste here. Okay. The same thing for standard error. Copy all 7 studies and paste. Then pay attention to what happens to the final plot. So that's it. The final plot is filled out. Let's see what the final plot looks like. So this is the final plot. And the question is whether this looks as symmetrical as you would want. If you want to take a more careful look, you can click it and you will see the study names. This is the mean difference that we input, the standard error that we input, and these are the mean differences, okay? And this is what the final plot looks like. This is a fixed effect estimate, all right? Does someone want to interpret this for us? Let me bring it up on the slide so you can. Anyone want to interpret for us? Can you go ahead? Yeah. We can't hear you yet.
All right, can you hear me now?
Yes, we can hear you now.
All right. Okay. Quickly from the forest plot, The diamond there shows that the result is in favor of the control, okay, from the pool estimate. And study number 1, okay, the first study there, Abioye 2021, is the one with the highest weight of 45.3%.
Yeah. Okay.
So
This is wrong, by the way. Remember, we had that issue last week too. Should be favors experiment. We swapped the order. So, but anyway, so we see the study IDs, right? We see the line of no effect.
yes.
Okay, that's the line of no effect. We see the x-axis scale. It goes from -4 to 4, right? We see the horizontal line through the boxes. What does the horizontal line through the boxes signify?
The confidence interval.
Confidence interval for each study, right?
Yes, each of the study.
Okay. What does the width of the diamond indicate?
The confidence interval of the pool effect.
The confidence interval of the pooled effect. So if you are going to write about this study in your paper, this is what you will write. Okay. Imagine all that effort just to be able to write this. Maybe you can add the confidence interval and say those who were exposed to media campaigns had 0.677 per day greater intake of fruits and vegetables than those who were not. And then you will add the confidence interval. You can say that this is statistically significant, but that's it. That's how you interpret the study. Now, there are all these other elements that we haven't talked about yet, and we'll talk about them in a moment, as we proceed. Okay. Any questions at this point?
Okay, I have a question, please. How do we take care of the this issue? I mean, the experimental on the wrong side and the control on the other side. How do we actually take care of it?
Okay, all right. It's actually fairly simple. So if you click here, this gears, right, which shows the settings. That's the icon that's often used for settings across a lot of programs. And you can click, it will bring up this box, and you can click each one and you can see the details for each box. Okay. Now, if you look, this is the left. It says favors experimental, but that's the wrong ordering for our question. So you have to think about each particular research question and where you expect the estimate to be. In this case, the left label should be favors control. And this should be favors experimental, experiment, or experimental arm. And if you click apply, you can see that this has changed. Okay, you can bring up the forest plot, and it looks exactly the way that we expect it to look. All right. So we can correct that, the slide. If you click here, you can copy and you can delete that. So if you look in the slide again, at least this slide that I have up on here, you can see that it's changed, favors experimental arm. All right.
Okay.
You have another question?
Yes.
Okay, go ahead, ask your question.
All right. Doesn't it look like we are the one trying to change the data? What if at the end of the result, we had the pool estimate on the left? Does it mean that we still have to shift the experimental arm to the left to actually to go with the result we want? I don't know if you.
Okay, so I understand what you're saying. I'm not sure why Revman does this, but the thing is that you have to understand the data that you expect to see based on each of these individual estimates, and even based on the pooled estimate, right? Because the pooled estimate is 0.67, which is on the right of 0. Do you see what I mean? Because 0.67 is on the right of 0. 0 is the null in this case. If we had something like minus 0.67, then that would be here. And because we understand, if you understand the meaning of that 0.67. The 0.67 means that this favors the experimental arm. And so the problem is just Revman labeling wrongly. I'm not sure why it does that. But that's probably an error that we're expected to sort of fix ourselves. Does that make sense?
All right. Yes, it does. Finally, please. I know this makes much sense, especially when we are having the effect from each of the effect from the individual studies on one side of the line. Okay, of course we know that at the end we have our diamond on that side, but I mean, wouldn't there be an issue if we are trying to, maybe if we have a study, okay, we have a meta-analysis with the studies having the effect on both sides of the line, and then we are trying to figure out which side is the experimental.
Which side it is. So we're not looking, so we're not looking at these estimates to determine what is correct. No. What we're looking at is this person, this number. That's what we're looking at. That 0.67 is the pooled estimate, and we understand that 0.67 is above 0. Okay? Because 0.67 is above 0 and 0 is the null, that is why we expect that it favors experimental arm. Here's the thing. If you did this in Stata, for instance, or R, it might not even report this for you, favors experimental arm. This favors experimental arm is something that you have to add based on your understanding of the study, based on your understanding of the relative risk structure. Do you see what I mean?
Yes, I can see.
Yeah, so it doesn't have anything to do with where the boxes and the lines are, the horizontal lines are. It's based on your understanding of the pooled estimate. Okay, all right, let's take another question. Teslim, you have a question?
Yes, I do.
Okay,
I'm trying to get the explanation right. Are you saying the pool estimate cannot be on the negative side from what you were trying to explain earlier?
I'm saying the pool estimate can be on either side.
Okay.
Yeah, but this pooled estimate is on the positive side.
Okay.
So because it's on the positive side, we will label this favors experimental arm correctly.
Okay.
We'll correct Revman that this is not the way to interpret the way it has written it.
Okay.
Yeah. I think someone else had another question earlier, but maybe it's addressed and we can move forward. Any final questions before we move forward from this point?
My question is, like in this case, this Revman report we are seeing, is it the right arm that is our control or the left arm that is our control? Thank you, sir.
Okay, excellent. So this right arm, this arm is the experimental arm, and this arm is the control arm. This is where the control arm will be. Okay, for this particular study, that's how we interpret it. It's not because we're finding significance, or it's because that's what the 0.67 means based on the way the studies are designed. That's what it means. Okay.
Okay, sir. Additionally, sir, sorry, sir. Closer to the null, is it control, or far away from the null is the control? So that when we're interpreting our result, we'll be sure that, okay, if we have 0.9, it's closer to, it's far away from the null. Or is it closer to the null? I don't know.
So it's not, okay, let me explain what the null does. It's not whether it's close, it's whether it's on the right side of the null or on the left side of the null. That's all.
Okay, thank you.
It's not whether it's close. So we're not saying whether it's here versus if it's here. We're saying whether it is on this side, okay, versus if it is on this side. And now my graph looks like a mess. This is what I mean. It's
Yeah,
whether it's on the right side versus if it's on the left side, and it's based on our understanding of this 0.67. If the value, the pooled estimate was above 0, then we know that it favors the experimental arm. If it is below 0, so if it's negative something, then we know that it favors the control arm.
I'm fine, sir. Thank you.
Excellent. All right, let's keep going. Now, this is the
excuse me, sir.
Yes.
All right, thank you for the explanations. Another thing I also saw is that you directly copied the variable, the mean and the standard mean, into the Revman. Is there a way of importing it like the way SPSS does? You can import directly without copying paste.
No, there is no way in Revman. Unfortunately, Revman is not a statistician's tool, so to speak. You know, it's a tool for any people who are like working without code. So that design impacts how they study the tool is used. Okay. So I'm just catching up on the comments in the chat. So someone said that I want to know if the main difference means that we firstly make the difference of the outcome level between the exposed groups. Yes. You take the treatment arm, the main in the treatment arm, you subtract that from the main in the control arm. Okay. And then, so in this case, we have already gotten that the mean difference, we've already gotten it by looking at the mean in the treatment arm and the mean in the control arm. That's how we got the 0.3. So that's what you will do for each study, and that's what we are pulling to get 0.67. Okay. Someone said, can we assume that once the pooled estimate is on the positive, it favors experimental, maybe like a rule of thumb? I want to say that it depends on the study that you have designed. Okay. If the experiment is designed to reduce something, all right. If the experiment is designed to reduce something, so maybe you're doing you're doing an exercise intervention and you want to reduce the BMI. This is where this will favor your experiment. It will be on the left side. If the experiment is designed to increase something, then it will be on this side. So it doesn't necessarily mean that if it's on the right, then it's your experimental arm. If it's on the left, it's your control arm. It depends on the aim of the study. Okay. So let me take that again. If you have a study where you're hoping to reduce the BMI, right, and your experiment is exercise, so that means that if the BMI reduces, then the mean difference will be on the negative side, right? Then this is where this will favor your experiment. If the purpose is to increase something, in this case, we're increasing intake of fruits and vegetables. If it favors the experiment, then that's an increase, and that's why you say favors experimental arm here. All right. The labeling is arbitrary. Excellent. That's what that's the word I should have found. The label is arbitrary. It's up to you to decide. Okay, please ask your question.
Yeah, so I wanted to just ask, is it like, I'm trying to understand it, and I don't know, is it like interpreting when you have odds ratio and the test results come out negative, you say the effects reduce the likelihood? Is it something like that? Can we say
that's
something?
Exactly, yes. It's something like that.
It makes it easier to understand.
Yeah, that's exactly what it is. If the mean difference is negative and the purpose of your study was to reduce the estimate, then you will write it based on that. So, you know, like you have to look at the specific situation before you determine what side of the study the experimental arm and control arm should be. It doesn't affect our pooled estimate because that's based on, you know, with the data that we obtain from primary studies. All right.
Apologies, sir.
Yes.
For the mean estimate here, I can see that we have like the confidence interval 0.18, for example. Okay, for Abioye now is 0.0. Did we impute this? We did
This
not,
one?
sir. Yes, sir. 0.0 then 0 to 0.6.
This is the confidence interval. So this is standard error, 0.15. So it's based on that standard error that Revman has calculated an estimated confidence interval. So it's not a perfect estimate, okay?
Okay.
But it's kind of close to what we would have obtained. Here, this is 0.12, but when Revman calculated it, it obtained 0.00 something. Maybe
Okay.
0.001 or something like that. Yeah.
Okay, thank you. Because I just looked at, I did a work sometimes where I actually compared the main change in the knowledge of the two groups, and I
Yeah.
reported the main difference, but did not report the standard error. So that means for anybody seeing that study won't be able to work with it for a better analysis.
Exactly. So if you report standard error, or if you report confidence interval, or if you report the p-value,
okay,
then
okay.
it's possible to work back and calculate the confidence interval. But for the p-value, you have to report the actual p-value, not less than 0.05 or less than 0.01. It has to be 0.54 or 0.00000123, something like that.
Okay, so here I reported the mean difference and the 95% confidence interval of the difference. So
And
that
that's
means,
going to be enough.
Okay.
Yeah, that's going to be enough. Yeah. Okay.
Thank you so much, sir.
You're welcome. All right. So let's keep going. So we can obtain the funnel plot for this study. So can somebody tell us if they think this is symmetrical or asymmetrical? Hello, yeah? Asymmetrical? Who is speaking? Abbas, okay, all right. Yeah, it's asymmetrical. We can hear you faintly in the distance. It's asymmetrical, right? You can see that there's two studies on the left, and then you have all these other studies on the right. That's asymmetry. It's very clear asymmetry, unlike the previous one where we were like, maybe it's asymmetry or not, but this is clearly asymmetrical. And this tells us, what does the asymmetry tell us? Anyone? Yes, Usman.
Likely a publication bias.
It tells us that there's likely publication bias. Excellent. But there might be other reasons for that asymmetry as well. We talked about small effect studies. Maybe there's some translation. It might be that maybe some of the studies that are missing.
Misclassification bias.
Misclassification. Yeah. Sometimes those are reasons why some studies might be
Will
missing.
this one be differential or non-differential?
So wait, hold on. Misclassification does not have anything to do with this issue here. Okay. And that discussion about differential or undifferential or non-differential, that has to do with the specific study estimates.
I didn't catch that.
That does not have anything to do with the asymmetry. The reasons why there's likely to be asymmetry, the most important one is publication bias. There's also small study effects where maybe some small studies were designed in a totally different way from the way that large studies were designed. Okay, that's another potential reason. Those are not as common reasons as publication bias, but they happen. Another reason could be that maybe some studies were published in another language, maybe Chinese, for instance, or increasingly we're seeing studies published in Portuguese and in Spanish. If you do a meta-analysis and you're an English language speaker, you don't have access to studies published in these other language, it could lead to publication bias, or it could lead to asymmetry like this. Okay, but the most common reason for asymmetry in a funnel plot is publication bias. Okay, if you don't remember any other reason for publication bias, that is publication bias. If you're curious about what misclassification is, you should review the EPI 101 notes, but very quickly I should say that misclassification happens when you are trying to classify something and you classify it wrongly. So maybe you're measuring hemoglobin, and hemoglobin is my favorite example because that's where I've done a lot of my work. So hemoglobin, you're measuring hemoglobin. In some studies, hemoglobin is classified into anemia using 11 grams per DL. In some studies, they have used 10. And that you see that in the literature. Some studies will use 9.5, some studies will use 12 and 13, depending on gender. Okay. If you think about the fact that some of these studies, some of them one study will take person A and classify that person as anemic. Another study, if that other study was done in the same population, will classify that person as not anemic, right? Depending on the threshold that was used, that could lead to misclassification. Okay, so that's just a quick look into it. But there's the question of whether this is differential or non-differential. I'm not going to go into that because that's not essential to this topic today. Okay. All right. So let us take a 4-minute break and then come back. And then when we come back, we will talk about standardized mean difference very quickly, and then we're going to heterogeneity. Okay, thank you. 4-minute break. All right, welcome back. Does anybody have any quick questions um, before we continue?
Yeah, hello. Good evening, sir. Good
Yes.
morning. I wanted to
Please
take
ask
your
your
back
question.
the interpretation of the results, please. Can you just come back a little?
This one?
Yes, this one.
Okay, which
So
part?
those who were exposed had 0.7677. So can we report this the same way we did the risk ratio and odds ratio, like subtracting one and then expressing it in percentage?
No, we cannot.
Can we do that with the
this
mean
is,
difference?
No, we cannot, because this is a difference. It's just higher or lower.
Okay.
With the relative risk and the ratio measures, we can subtract from one if it is less than one, or we can multiply by 100. Like there's those types of approaches that you're talking about, but that's for ratio measures. For difference measures, just exactly, we don't subtract. We just report it as is greater than or less than, depending on if it is negative. If this were negative, you can say 0.677 per day less than, or lower intake of fruits and vegetables, something like that. And you don't have to say minus 0.67 greater than, right? So you interpret it based on, if it's a negative sign, then you say it's lower. If it's a positive sign, you say it's greater. That's all. Okay. Thank you for that question.
All right, thank you.
Yeah. All right. So standardized mean difference. So remember we said that if you have a mean difference, and we talked about what mean differences mean, and you want to, but you're using mean difference for outcomes that differ. You have multiple different kinds of outcomes. Those outcomes are exactly the same based on some larger concept, right? But they're different in the particular measure, the units that was used. And I gave the example of adiposity, where adiposity can be measured using BMI, can be measured using fat-free mass, can be measured using lean mass. There are other ways that this can be used again, and I talked about the depression example, where maybe the outcome, some people use CESD, some people use Hamilton, some people use GHQ-12, some people use what's that one? SF-36, and you have some idea or maybe some understanding that these tools measure depression. They don't all do. But because they're measured using different scales and you want to pull them together, right? You have to be sure that what you're measuring is still the same outcome, depression. And then you can use those tools. And there's multiple different tools you measure depression. But because you're saying if depression is what I'm measuring, but they're measured using different scales, you can use a standardized mean difference. And what you do is that you standardize each estimate. You take the mean difference and you divide it by the standard deviation, and you will get your standardized mean difference, okay? So I can show this to you because these are just made up numbers, right? In this Excel sheet. You can see that here what we did was that we have this mean difference and we just divided it by the standard deviation, and we use that to get the standardized mean difference. And the same thing for the lower confidence interval, the upper confidence interval, and then we use that to obtain a standard error of the standardized mean difference. Okay, all right. So you can do exactly the same thing that we just did, where you just input, instead of inputting just the mean difference, you input the standardized mean difference here, and you will obtain the standard error. But let's just go through it so that you can see what I'm talking about. Okay. So first of all, let's add a new outcome. And this outcome is going to be a generic inverse variance as well. All right. next, and we'll call this, what did we call this one? We call this one, okay, all right, so outcome. So we'll call this one standardized mean difference using pre-calculated data. Next, so here you will click standardized mean difference, and then you click next. You click next, and then you click finish. All right, let me go back so that you can see what I'm saying. So when you right click here on this comparison, it will ask you to add outcome, and then you choose generic inverse variance because this is pre-calculated data. You click next, and here we're saying standardized mean difference, pre-calculated data. You want to use an informative outcome name so that you can always figure out what you're doing. And you click next, you click standardized mean difference, you click next, okay? You leave this the way it is unless you want to enter the sample sizes, and then you click next. And because of all the issue that we have been having, we can just correct this now because we understand the direction that we're interested in, okay? And then you click next. Now you add the study data and you click continue. Now, if you're adding study data, it will bring up the studies that we already have specified. We did that last week. You select all the included studies, you click finish. And then because we have pre-calculated the standardized mean differences, you just copy that and you paste it in Revman. Do the same thing for the standard error of the standardized mean difference. Okay, you copy that and you paste it in Revman. And this is what your forest plot looks like. Remember that the forest plot, the default is that the scale is 100 and you can change that scale. To change the scale, you click this gear button or this gears icon or whatever, and you can change the scale on graph. Okay, so you see here it's 100, that's why it goes 0 to 100. But what's more reasonable is maybe something like, let's try 5 for starters. So here you can see that we used 5 when it was mean difference, but even now 5 looks so large. It's too wide. So we can use something like maybe 2 or 1. All right, and you apply. Now you see what it looks like. Now this looks more like a reasonable scale to use for this plot. And then you click OK. Okay. And this is what the forest plot looks like. So the forest plot looks very similar to the forest plot for mean difference because we included the same studies and we just calculated the standardized mean difference for each one by subtracting its mean difference by the standard deviation. So the shape of the forest plot looks the same, but the numbers are different. All right, the numbers are different. And then earlier we obtained a pooled mean difference of 0.67. Now we have a pooled mean difference of 0.12. Okay, and we can just show what that looks like. I can show what that looks like. I'm just correcting it very quickly in the presentation. Okay, can someone tell us what we're looking at? Anyone want to take a shot at interpreting? Anyone?
Yes, hello, sir.
Yes.
It's Usman Umar that is talking.
Okay.
So first of all, we look at the study IDs as usual on the left.
Yeah.
Then we look at the line of no effects, which is drawn. Then from the 0 Then we look at the left axis, and then we look at the pool estimate, which is more in favor of the experimental group.
Yeah.
And then we look at the confidence interval of the individual studies, which are the horizontal line that run across the squares. And then we'll look at the weight of each of the studies. It's not, I think this, the fourth study look, or is it the first or the fourth, look to me that they carry more weight.
Yeah.
Yes, I think when we look at the values, it has like 36.2%. That is the fourth study. Yes. And then we can look at the standard mean difference, that is the overall, which is 0.12, and the confidence interval, which is significant because it has not crossed the null value, which is 0.
Which is 0. Excellent. Excellent.
Yes.
Thank you very much for that. And now, here's a question to you.
You're welcome, sir.
Because remember that the last one we said that the units were in servings per day because we're looking at fruits and vegetables, right? What are the units here for standardized mean difference?
Yes.
What units do we use?
There is no units because it's the standardized now.
There is no unit, exactly. So yeah. So what we say is that we say that 0.12 standardized units. That's what we do. That's how we report it. So you will say that those who were exposed to media campaigns had 0.12 standardized units, or you say units of standard deviation, greater intake of fruits and vegetables. So it's a little harder to interpret. So it's not a favored approach. So you might not see this very often in literature, but sometimes if you absolutely need to do a standardized mean difference, then you consider it. And if you do that, then you have to report the units correctly. So we have a question. Dr. Frank Obi, please go ahead.
Yeah, thank you very much for this interpretation. I wanted to confirm, is it right to say it does not have units, or is it that standard deviation is the units?
So it's kind of the same. So in the sense that it's not a typical unit like kilograms per meter squared or liters, which is the typical units that we think about. So the correct thing is to say that standardized units are the units, but you can also understand it as saying you don't have the traditional unit system. I think that's what he was getting at when he said that it doesn't have unit. It doesn't mean that when you report it, you have to say that it's 0.12 standardized units so that the person understands, the reader understands that you have done some standardization to the values. Next question, Usman.
Okay. Sir, please, I need a little some clarification, because I was thinking that when you use the standard mean difference, you are going to use the standardized, is it standard error or something like that?
So you're using the standard deviation.
Okay.
Yeah, so you use the standard deviation. So you divide the mean difference for each study by its standard deviation to obtain the standardized mean difference. So if you remember, for the first study, the mean difference that we got was 0.3. And so when you divide that by the standard deviation, you obtain this number.
All right.
And that's what you do for each study. Yeah.
Okay. So, sir, are we also expected like the column for the standard error? Like maybe are we using the same standard error, or we are also going to impute the standardized like standard error?
Yes, exactly. So what you're going to do is that, let me show it to you. So you will obtain the standard mean difference, like I said, which is by dividing the mean difference by the standard deviation. Okay.
Yes.
And then you will divide the mean difference, the lower confidence interval of the mean difference, by the standard deviation to obtain the lower confidence interval of the standard mean difference.
Okay. Okay.
Then you take the upper confidence interval for the standard for the mean difference. You divide that by the standard deviation, and you obtain the upper confidence interval for the standard mean difference. Then you use these two numbers to obtain the standard error of the mean difference.
Okay, sir. Okay, I think what confuses me is the
How is it by multiplying it to get that standard mean difference?
Yeah, that's actually my
No,
question.
so you divide. Okay, so if you have a lower and a lower confidence interval and an upper confidence interval, to obtain the standard error, what you do is that you subtract this minus this divided by 3.92. And 3.92 comes because if you remember, we say that the confidence interval, we obtain the one side of the confidence interval by saying 1.96 times standard error. All right.
Yes.
Now we have two standard errors, one standard error on the right, another standard error on the left. So we multiply that by 2. 1.96 times 2 is 3.92. So if you just subtract upper minus lower and divide by 3.92, you will obtain the standard error of the standardized mean difference. Same thing, the same way that we got the standard error for the mean difference. Okay. So here, if you look inside this,
okay, sorry,
if
I
you
wanted
look
to ask,
inside
do we
this
need to calculate
Excel,
all this? Or is there an easier way of getting it without doing all this calculation?
if you want to use Revman, you have to calculate it yourself. Actually, most softwares, if you want to use most softwares, you will have to calculate it yourself. And in any case, even if you're not calculating it yourself, and we'll talk about that when we get to R, okay, you have to understand what the software is doing. So that because sometimes, you get errors, you'll be able to catch errors. These tools are not perfect. Sometimes there are errors, or sometimes you haven't perfectly understood how it's working. And if you understand the fundamentals of what you're expecting to see, you will know when you're doing something wrong or when you're obtaining something wrong.
All right, thank you.
Yeah, you're welcome. All right. Anyone else? So let's keep going. So we don't have a lot more time.
Back to the interpretation of the result.
Okay.
I think this is not friendly for public health passing information. I mean, 0.12 standardized unit data intake.
So yeah, you're absolutely right. But you see, there are some cases where this is what we do in public health. So I'll give you an example. Weight for height z-scores. Okay. Weight for height z-scores, they are already standardized. Right? We're not using a typical assessment like maybe weight in kilograms. So when we interpret weight for height z-scores, and we use weight for height z-scores every day in pediatrics, when we look at the weight of a child, we look at the height, and then the WHO has those good charts. And those good charts, they're based on weight for height z-scores. So that's an example where we're using it on a daily basis. A lot of people are not thinking about it in this way. I'm not saying 0.12 standardized units because you're looking at it from a chart. And if the child is going higher or going lower, but this is what it is based on. It is a form of standardized units. Okay. So just to say that even though it's not easy to immediately grab, but it's not something that is absolutely senseless. We are using standardized units in our practice, even if we don't realize it. Okay. All right. So let's keep going.
Okay, sir.
Yeah.
Yeah. If I want to communicate these results to, let's say, policymakers.
Yeah.
What will I tell them? Like these 0.12 standardized units. How will it be interpreted so that they will understand what they're saying?
So that it's certainly a challenge. So, but you would focus on the direction, okay, which is that media campaigns are leading to increased intake of fruits and vegetables. That's one. Now, for you to also capture the standardized unit, you will have to explain to them what standardized units are. You know, you will have to explain in some way. You don't have to go into so much detail about it, but you will have to give some quick understanding of what standardized units are to be able to say that 0.12 is large enough. You know, and again, there is no scale, for instance, to understand what large enough means, right? But 0.12 is meaningful depending on where you're deriving it from. I want us to move along so that we don't, so that we can actually get through this meta-analysis of continuous outcomes, and then we can decide whether we want to get to heterogeneity or not today. But at least I want us to make sure that we finish the continuous outcomes. Okay, all right. So the key takeaway is that communicating standardized mean differences is challenging. There's no way to simplify it without going into an understanding of what they mean, what the units mean. But oftentimes, if you just focus on the direction, that gives an idea of what's happening. Okay. All right. This is the same forest plot, so I'm going to skip it. So weighted mean difference based on raw data. So we look at pre-calculated estimates. Now we want to look at raw data. And it's often useful to use raw data if you have raw data, because what if you don't fully understand the drama that is happening behind the standardized mean difference, all that estimation of the standard error, you know, like that Excel sheet that I showed you. If you just have the raw data for all the studies, you can just input the raw data directly. So if you go back to Revman, okay, so we will create a new outcome. So to create a new outcome, you click on this comparison, and then you say add outcome. In this case, because you're using raw data, you click continuous. If you click continuous, you click next, okay? So remember that when we use pre-calculated data, we use generic inverse variance, but here you will use continuous. To use continuous, this is the data that you need is the mean, the standard deviation, and the number of participants in the experimental and in the control arm. Okay, so you click next. So now you have to label the outcome. So I will call it weighted mean difference raw data. So that's informative enough. With next, here it says the inverse variance, fixed effect, and we can choose random effect if we want. Mean difference again, click next. And here, totals, subtotals, click next. Here, I'm going to change it because we know what we expect, that the control is on the left side, the experimental arm is on the right. So I will leave this, so the scale, I'll change this to 5 because if you remember we saw that 5 was the scale that made sense. So typically you will try it out first and then adjust the scale. I showed you how to adjust it and then click next. And then here you will add the study outcome and then click continue. Then it will ask you which studies you want to include. If you hold it down and select all, then you click finish. So now we have this, and it was hiding all this information. Okay. So you can see that we need 6 data points for each study: the mean, the standard deviation, the total for experimental arm and for the control arm. All right. So you go back to your Excel. In the Excel sheet, we have the data that you need. All right. Again, the first thing you need is the mean and the standard deviation. So this is the mean for the experimental arm, the standard deviation. This is the mean for the control arm, the standard deviation. Okay. And so you select all these, you paste it in Revman. So if you only had these and their ends, you'll be fine. You don't need the pre-calculated. You know, these are just alternative approaches. So here you paste, And then you go back, you copy the standard deviation. You have to make sure that you're copying the right thing. Then you paste that. You copy the mean of the control. You paste that. You copy the mean of the standard deviation of the control. You paste that. Okay. Now we need the ends, the total number for control. And if you scroll all the way to the left, okay, scroll all the way to the left. Here we have the number in the exposed, that's the treatment arm, and that number in the unexposed. Okay. So the number in the exposed, you copy that, you paste, that's the experimental arm. Then the number in the unexposed, you copy that. I'm using Control C to copy. I'm just using Control V to paste. And now you have your forest plot. Okay. So let's look at the forest plot. And you can see that it looks exactly the same thing as what we saw before, because we use the exact raw data for that study, It doesn't mean that it will always look exactly the same, depending on whether the raw data and the pre-calculated effects, if the pre-calculated effects are adjusted for confounders, okay, you might not get the same numbers. I think I explained that when we saw it for the dichotomous or multiplicative outcomes. If the pre-calculated effects are adjusted for confounders, they will not be the exact same. But if they are not adjusted, then they will look exactly the same as if you use the raw data. All right. So this is what this looks like. Any questions? Any questions at this point?
Yes, I have a question. Just
okay.
An observation here. So when we use the pre-calculated data, the color on the forest plot was red, but when we use the raw data, the color was green. Is there any reason for this?
I think that's just Revman playing around. I didn't even notice that before. Thank you very much for pointing it out.
Okay.
Yeah, just Revman playing around. Maybe just so that you can easily see that this is what you're using pre-calculated and raw data. But that's a very good observation. Thank you. Okay, so this is what it looks like. I'm not going to ask you to interpret this because we've interpreted a couple times. But this is what you can do the same thing for the standardized mean difference. But what you will do is that if you input these numbers like this, okay, pay attention. You have input the numbers like this for raw data, and you want to obtain the standardized mean difference. You have a very simple thing that you will need to do. You click this button that says MD, and it changes to SMD. That's all. If what you wanted to obtain, so let me explain how. So say for example, the studies that you looked at, right? You had these 7 studies, and some of them they had reported the exposed and they had reported the mean differences, based on BMI. Another one had reported based on lean body mass, based on different measures, and you want to look at that as a measure of adiposity. You will enter the numbers like we did raw data, but yourself, based on your understanding of the papers, that this one is maybe BMI, and this one is lean body mass, okay? And this is BMI, and this is lean body mass, and maybe this is fat-free mass, okay? And the numbers are, and these are the numbers that you obtain. So you input this in the Revman, but you know that they are not exactly the same scale. So you know that you have to use the standardized mean difference. Okay, so when you enter the numbers, you do not report the mean difference, you report the standardized mean difference. So all you needed to do was click this MD and it will change the standardized mean difference. And then you can edit the scale using that gear button, you know, and so maybe here you change this to 1 or to 2, depending on what you prefer. And now this is the forest plot that you present. Is that clear? Well, do we have questions? So the question of whether to use mean difference or standardized mean difference depends on the numbers that you obtain from your study, right? It doesn't depend on whether it is pre-calculated data or raw data. Or yeah, pre-calculated or raw. Okay. So this is a very important thing to note so that you're not misleading the readers. All right. So that's where we are with continuous outcomes. I have maybe a few more slides to explain heterogeneity and subgroup analysis in Revman, but I am inclined to not continue at this point and to schedule a different session for it. What do you folks think? If we start now, we might go for another 30 minutes or maybe a little longer. I want to hear what you think, and then we can decide very quickly. So if you think that let's keep going, can you do a thumbs up? Or if you think let's not keep going, I think maybe there is a thumb down button. I'm not sure. Or you can add comments in the chat. Okay. All right. Yeah, so I was so we do have, so I'm looking at the schedule. Let me show you the schedule for the class. And it looks like we might have some extra time we might be able to so this is a schedule that we are working on. This is not final. This is like an update. Because now we're able to do SPSS one time. And we are doing a repeat of that SPSS session tomorrow, right? And then we're going to start R next Saturday. But we have a free session here, and we have a free session here. You know, and we might be able to use either of these days to do heterogeneity. We might move the R such that we don't get to heterogeneity in R before we teach Revman. Or we might, you know, maybe use the 11th. Unfortunately, we can't do next week because I'm not going to be available. But we can do the 11th, and Dr. Banigbe will teach R next week. But I think we should reschedule so that we give people enough time to internalize what has been taught, and you can come back with questions. So by the time we come back to Revman the last time, you know, you can bring all your other questions that you have and we can address them. And then we can also go into heterogeneity. What I want to make sure that we do is that I use that session to explain concepts in heterogeneity before we teach it in R. Okay. So yes, I agree that we should reschedule and we can close the class early. So does anybody have any questions? Once we finalize this schedule, I will send it out. You know, this is an update that we're making because of changes in our schedules. Once we finalize the schedule, I'll send it out to everyone, so you don't need to like screenshot or anything. Any questions? Or this is perfectly clear, you're excited to go start doing your continuous outcome analysis. Someone said, what time is tomorrow's session? The same time as we started today. So it depends on your time zone.
Yeah, I'm still concerned with that favor and control side. I think we need to find out how to do it better.
This one, so basically, here.
Yeah.
Okay. All right. Okay.
I think we're doing something wrong. Maybe the input of the data, or we are supposed to. It's just confusing.
Yeah, I agree with you that it's a little confusing, but it's the issue is that it's arbitrary.
Yeah.
The reason why it's crystal clear in my mind is because I learned meta-analysis in Stata, okay, for the first time. And in Stata, you don't even have these options. You're the one who writes it in. So Revman is only being helpful by suggesting to you that you could write it like this: favors control, favors experimental. So in Stata, you're the one who's going to click that right side and even type it in. So you will have to edit it. Stata doesn't even have the option unless you use code, right? For you to add it, you have to go type it in using maybe picture. What these tools that are available on your computer? I think picture, or what's the other one? Paint, right? So you will often take the forest plot and put it in Paint, and then use that to type in what's it favors. Does it favor experiment or favor control? So it's arbitrary. It depends on your understanding of the direction of the exposure and the outcome. Okay. All right. Someone said, can you show once again how to check the forest plot? Do you mean how to interpret or how to find it? So how to find it? Okay. So on the this is on this Revman interface, right? If you see these small icons, this row of small icons, if you go 1, 2, 3, 4, this one is the forest plot. This next one is the funnel plot. And if you look at it, the icon itself looks like a forest plot. And the same thing for the funnel plot, the icon itself looks like a funnel plot. If you look very carefully. So the only thing you can do is just try them out. So if you click this one, the forest plot will open. Wait 1 sec. So if you click this one, the forest plot will open, right? You can close that. This is the funnel plot. And if you wanted to copy it, you can click this button. It will copy and you can paste it in Microsoft Word, right? Or you can save and you can change the type, and you can save it as maybe a PDF or a PNG file, which is like an image file, and save it wherever you want on your computer. So multiple ways to get it out. But to take it out of, or to find it on the interface, you click this icon that looks like a forest plot, and the forest plot will appear. Or if you click this icon that looks like a funnel plot, the funnel plot will appear. All right. Excellent. Any other questions?
Yes, sir. Sorry, this is probably a very basic question, just something that confuses me a bit. Now, we've been talking about the relative risk odds ratio, and my guess is that you get these things from statistical tests. So, this is what I think I know, so you can help clarify. If you do a logistic regression analysis, it's going to give you odds ratio.
Correct.
Now, and that is what we are using here, right? Now, what test do you do that gives you relative risk? I'm really confusing this, the odds ratio, relative risk, and effect size. Sorry. Thank you, sir.
Okay, excellent. I'm going to find a set of slides that can help us just go through it very quickly. Okay. All right. Let me share this slide with you. Swap. Okay. All right. So There are different types of effect measures. We have the relative risk or the risk ratio. We have the hazard ratio or incidence rate ratio, and we have the odds ratio. Okay. And if you do a logistic regression, you will obtain odds ratio. Okay. If you do a Cox proportional hazards model, you will obtain a hazard ratio. All right. There's some other methods like a log binomial model. Forgive my typing. I'm trying to write it using the mouse. So a log binomial model will give you a relative risk or a risk ratio. Okay. Now, you can also calculate all of these estimates, or at least the risk ratio and the odds ratio from the 2x2 table. This is what the 2x2 table looks like. And that's the same thing I've been looking at: the exposed, the case, the non-case, the unexposed. And we said that you can find the exposed case, the exposed non-case, the unexposed case, and the unexposed non-case. So you have A, B, C, D, and you can input these into this formula and you get the risk ratio. You can input this into this formula, you get the odds ratio. Now, in this meta-analysis that I've been doing all day, we have been using the risk ratio. Sorry, the meta-analysis that we have been doing, not all day, last week, we used the risk ratio. But you can use the exact same method for odds ratio. The only thing is that you shouldn't add them together in the same meta-analysis, okay? Don't add them together in the same meta-analysis. But you can, the way that you do the meta-analysis of the risk ratio, where you have maybe 7 risk ratio estimates, is the exact same way that you do the meta-analysis of the odds ratio. Say maybe you have 7 odds ratio estimates. Okay? It is the exact same way that you will do a meta-analysis of hazard ratio or incidence rate ratio if you have 7 hazard ratio estimates, because these are all what? Ratio estimates. They're all ratio measures. And sometimes we talk about effect measures. Effect measures are a large group that include ratio measures, difference measures. And these ratio measures are also sometimes called multiplicative, while the difference measures are called additive. These are all just different terms that we use depending on what we're thinking about, the multiplicative versus the additive, and the different risk ratio versus odds ratio. So yeah. But today we looked at difference measures. Okay, we looked at difference measures. In this plot, we have the risk difference and the incidence rate difference, but today what we looked at is the mean difference. Okay, is the mean difference. What we looked at is the mean difference. But if we had the risk difference, we would have done it the exact same way that we did the mean difference. But no standardization, okay? No standardization, but we would have done the meta-analysis the same way as we did the mean difference. Okay? But not for if we had raw numbers. So like if you had raw data, you can, the risk difference is more complicated in some ways. So let's just leave it. But the pooled meta-analysis of the mean difference, if we have mean difference across 7 studies, you can pool the mean difference and obtain the pooled mean difference. I hope this is clear. I didn't just now confuse you a little more.
Thank you. I'll go over it again, but I think it's better now.
All right. So this is what Aminu was getting at earlier when he asked if we can subtract 1 from the result. And I said that that's useful if you're interpreting the ratios. If it's between one greater than 1 and less than 2, you can subtract 1 and you can interpret in percentage. Okay. But yeah, if you review the EPI notes or the slides, this is exactly from there. All right. Thank you very much. Any other questions? I'm going to assume that we don't have any other questions and that this is perfectly clear. All right, folks. Thank you very much for spending your Saturday with us. We will share more information about the next set of lectures or live sessions as we go maybe during the week, because we still have to finalize our schedules and then we'll let you know. But tomorrow we'll have the SPSS session. And it's basically a repeat of last week's session. So if you attended last week's session and it's very clear to you, you probably don't need to attend. Or if you want a refresher, then we look forward to seeing you tomorrow. Or if you didn't attend last week's session, then it'll be great to see you as well. All right. Excellent.
Thank you, sir.
Thank you very much. Okay. All right. So we'll talk about that when we get to it, the vigilante.
Thank you very
Enjoy
much.
the rest of your day. Yeah. It's okay.
Thank you very much. Thank you.
Yeah.
Thank you very much.
Bye.